Welcome to Tech Skill Hub's Beginner Machine Learning Lecture 9. Today we're going to do a super duper deeper dive into dimensionality reduction. This is a crucial concept in data science and machine learning. You need to know this one really well. We have emphasized in more than one of our lectures that dimensionality reduction is aimed at simplifying datasets while preserving their essential characteristics. Today we should get in the weeds and cover the fundamental principles, techniques and applications of dimensionality reduction. Let's get this bad boy started. So first things first, a reminder. What is dimensionality reduction? Dimensionality reduction refers to the process of reducing the number of random variables under consideration. This allows us to obtain a set of principal variables. It is particularly useful in high-dimensional datasets. As we talked about last time, high-dimensional data refers to datasets with a large number of features or covariates, often exceeding the number of independent samples. This type of data is common in statistical research and poses challenges in variable selection and model selection due to its complexity and size. The number of features or dimensions can be overwhelming, leading to issues such as overfitting, increased computational cost, and difficulties in visualization. We begin with a big problem with big data, and we solve this by carefully reducing it. So let's talk more about why is dimensionality reduction important. Well, one, it improves visualization. By reducing dimensions, this allows for easier visualization of data, especially in 2D or 3D plots. And two, reduced overfitting. Remember, overfitting is when the model trains on the training data so well it kind of memorizes it, and so it stinks at new data. By simplifying the model, dimensionality reduction can help mitigate overfitting, leading to better generalization on unseen data. And three, how about enhanced performance? Because with fewer dimensions, we can have faster training times and reduced computational resources. Finally, four, noise reduction. Noise in machine learning is unpredictable or random fluctuations in data that can make machine learning models less accurate. Dimensionality reduction can help in filtering out noise and irrelevant features, improving the quality of the data. Does all of that make sense? Good reasons to use it, right? So what are some common techniques for dimensionality reduction? We mentioned some briefly last lecture, but we need to cover them a little deeper. Let's start with good old principal component analysis, or PCA. PCA is one of the most widely used techniques for dimensionality reduction. Interestingly, principal component analysis was introduced by the mathematician Carl Pearson in 1901. That's old. It transforms the data into a new coordinate system where the greatest variance by any projection lies on the first coordinate, which is the first principal component, the second greatest variance on the second coordinate, and so on. It examines the interrelations among a set of variables. It is also known as a general factor analysis, where regression determines a line of best fit. Here are some steps. 1. Standardize the data. 2. Compute the covariance matrix. 3. Calculate the eigenvalues and eigenvectors. 4. Sort the eigenvalues and select the top k eigenvectors. And 5. Transform the original dataset, that is PCA. Now let's dive deep into T-distributed Stochastic Neighbor Embedding, or t-SNE. Remember that t-SNE is particularly effective for visualizing high-dimensional data in lower dimensions, typically 2D or 3D. It focuses on preserving the local structure of the data, making it suitable for clustering and visualization tasks. What are some key features? How about nonlinear dimensionality reduction? Unlike PCA, which is linear, t-SNE can capture nonlinear relationships between data points. And t-SNE preserves local relationships while distorting global relationships. t-SNE prioritizes preserving the distances between nearby data points, making it effective at revealing clusters and local patterns within the data. It is widely used in fields like bioinformatics, image analysis, and natural language processing to visualize complex datasets like gene expression profiles, image features, or word embeddings. There are several steps in t-SNE. 1. Calculate pairwise similarities. Compute the distances between every pair of data points in the high-dimensional space using a distance metric like Euclidean distance. Based on these distances, assign a higher probability to pairs of points that are close together and a lower probability to distant pairs. 2. Construct probability distributions. Create a conditional probability distribution for each data point where the probability of selecting another point as a neighbour is based on their similarity. This is often done using a Gaussian kernel where points closer to a given point have a higher probability of being considered its neighbour. 3. The perplexity parameter. Adjust the standard deviation of the Gaussian kernel for each data point to control the perplexity, essentially how many neighbours are considered important for each point. 4. Initialize low-dimensional representation. Randomly initialize the positions of data points in the lower dimensional space, typically 2D or 3D. And 5. Iterative optimization. Calculate a similar probability distribution in the low-dimensional space based on the current positions of the points. Use gradient descent to minimize the Kullback-Leibler divergence between the high-dimensional and low-dimensional probability distributions, iteratively adjusting the positions of points in the lower dimensional space to better represent the original relationships. Finally, visualization. Plot the final positions of the data points in the lower dimensional space to visualize the structure of the high-dimensional data. That is a deep dive into t-SNE. So now let's talk about linear discriminant analysis, or LDA. LDA is a supervised dimensionality reduction technique that aims to find a linear combination of features that best separates different classes of data by projecting the data onto a lower dimensional space, effectively maximizing the separation between classes while reducing dimensionality. You might ask, what are the applications? It is often used in classification problems where the goal is to reduce dimensions while maintaining class separability. Here is how you LDA. Wow, that sounds like a dance move. 1. Calculate class means. For each class, compute the mean vector of the data points belonging to that class. 2. Compute within-class scatter matrix. This matrix represents the variance within each class. 3. Compute between-class scatter matrix. This matrix represents the variance between different classes. And 4. Find the projection vector. Solve an eigenvalue problem to find the linear combination of features, projection vector, that maximizes the ratio of between-class scatter to within-class scatter. That is LDA. Finally, let's talk about the autoencoders technique. As we talked about last time, autoencoders are a type of neural network used for unsupervised learning. So they are a specialized class of algorithms that can learn efficient representations of input data with no need for labels. Autoencoders consist of an encoder that compresses the input into a lower dimensional representation and a decoder that reconstructs the original input from this representation. The advantage of autoencoders is that they can capture complex non-linear relationships in the data. Here are the steps. 1. Defining the input data. 2. Encoding the input data into a lower dimensional latent representation using an encoder network. 3. Decoding the latent representation back into a reconstructed output using a decoder network. And 4. Training the entire autoencoder by minimizing the difference between the original input and the reconstructed output, using a loss function aiming to learn meaningful features from the data. Essentially, the autoencoder tries to copy the input by compressing it into a latent space and then reconstructing it, forcing it to learn important features of the data in the process. So let's talk quickly about some of the applications of dimensionality reduction. How about image processing? We can reduce the number of pixels while retaining essential features for tasks like image recognition. How about natural language processing? We can reducing the dimensionality of word embeddings or document term matrices. And a fan favorite, genomics. by analysing high-dimensional gene expression data to identify patterns and relationships. This may be the coolest use. For instance, say we are visualising complex high-dimensional data like gene expression patterns in a biological sample, allowing researchers to identify distinct cell types or disease subtypes by clustering the reduced data points in a 2D or 3D plot, effectively revealing hidden patterns that wouldn't be apparent in the raw data. Finally, in finance, we can do risk management and portfolio optimization by reducing the number of financial indicators. In conclusion, dimensionality reduction is a powerful tool in the data scientist's toolkit, enabling the simplification of complex datasets while retaining their essential characteristics. Understanding and applying these techniques can lead to better model performance, enhanced visualization, and more efficient data processing. As we continue to explore the vast landscape of data, mastering dimensionality reduction will be key to unlocking insights and driving informed decision-making. So you can see that we are not always making things more difficult. After all, we are capable of dimensionality reduction, right? And as Indian comedian Kapil Sharma say, simple things make me very happy. Till next time, have a stellar day. Please like and subscribe for the sake of Tech Skill Hub and all Indian comedians everywhere. This is Ethan, signing off.
Why's the world gotta start so early in the morning, like 6 a.m. my alarm goes off. I wanna not think the alarm was made a bigger mistake. I wanna beat the guy who made her to punch him in the